Today we'll touch upon this intergalactic medium or the IGM and a little bit of early galaxies. So, if you look at early galaxies of the IGM, you are looking at high redshifts. So you have to have some sense of cosmology in order to appreciate this stuff. So I don't know if you guys have done the FRW metric and the solutions of that metric, and concepts like luminosity distance or angular diameter distance. Right. So all of this can essentially be done in the Newtonian language, and that's all is needed for appreciating like cosmology in the context of IGM and galaxy formation. And it's actually extremely simple. It's sort of, so you have to have a sense of the solutions of the FRW metric, and since we know the cosmological parameters now in the lambda CDM context, it's actually extremely simple. It's flat, so you don't even have to bother about more general parameter space. I can actually do that a little bit of FRW metric as applied to galaxies at high redshifts. Okay, I'll not really go into details of how you get those equations and all that, but I'll just sketch, right, the solutions. The equation that governs the evolution of the universe as a whole is Einstein's equation. But if you assume isotropy and homogeneity, you have this FRW metric, or Friedman, Robertson, Walker metric for the evolution of the universe. Okay, in that interval ds squared is given by c squared dt squared minus a squared dx squared plus dy squared plus dz squared. Okay, this is metric of space-time for this FRW solution of Einstein's equation. Okay, so it's actually extremely simple. All you have is this time-dependent g mu news. Okay, and these are called co-moving coordinates. So you will actually come to the, I don't know if you have already done it in this course that you're doing. You have not looked at the solutions perhaps, but you will do this. And so the picture is, right, we already encountered Hubble's law that the universe as a whole is sort of expanding. Okay, so if you had a little volume like this at an early time, with time, this volume expands isotropically to bigger and bigger size, right? So this t is called cosmic time, and these are co-moving coordinates, right? So this is the physical picture, right? So you can actually say this is 0, 0, this is 1, 0, this is 0, 1, and 1, 1, right? So these are the coordinates. These are co-moving coordinates, right? So I mean, even after it has expanded, the coordinates remain the same, right? Except that the physical sizes become a times the a times 1, right? So with time, if things are just co-moving with the space-time, they just get expanded. Okay, so for most of the applications, co-moving coordinates are very useful because it sort of takes out this trivial evolution of the universe, which just means that everything which was sort of closer together just moves far apart, right? So you generally you deal with the co-moving coordinates in cosmology, but it's sort of easy to go from one to the other. For using this as a dynamical equation, you need to solve. So this form of the 4 interval is just given by symmetry arguments, right? And this actually assumes flat space. That is, there is no curvature to space-time, and this is actually consistent with the cosmological parameters that we have now. So we are not doing the complicated curvature parts, but this is what's most relevant to us. But perhaps in the cosmology, the GRN cosmology course, you will do that. Need to solve for A as a function of cosmic time, right? A is a function of time, because that's what determines how the background space expands with time. The equation for that is given by this, A naught by A whole squared is equal to 8 pi by 3 g times rho, right? So this is the one of the Friedmann equations for flat FRW universe. So this is how A changes with time. Rho is the matter density, basically matter sort of energy density of universe, right? So universe, so rho consists of matter, radiation, and dark energy. So rho is equal to rho matter plus rho lambda plus rho radiation, right? So these are the principal components of matter energy, that we consider. Now, we already said that we are doing flat universes. So what it means is that the density is equal to something called the critical density of the universe, and that's just 3h squared by 8 pi g, where h is the time-dependent Hubble parameter. H is defined as a dot by a. Right? The value of a dot by a at the current time is h naught, which is 70 kilometer per second per megaparsec. But a is in general a nonlinear function of time. So basically, what it means is that this density, the sum of the densities of all the matter in the universe, is equal to the critical density of the universe. So this is essentially rewriting this equation, right? That's nothing but h squared. Right? You're saying that rho is equal to 3h squared by 8 pi g. I mean, I'm just saying rho equals rho critical. That comes from the requirement for a flat universe. Okay. So what about these densities? So normal matter, as the universe expands, the density of normal matter decreases. If you have the same amount of matter and the universe has become bigger, the physical density of that matter goes like 1 by a cube or a cube. Basically, a increases with time, 1 by a cube decreases with time. So a is called the scale factor, right? And by convention, a is taken to be unity now. At redshift 0, the scale factor of the universe is 1. So at early times, the scale factor was less than 1. The size of the physical size, you see, is a times the coordinate size of 2 points, separation of 2 points. So a is scale factor, and a is equal to 1 plus z inverse, where z is the redshift. And so at redshift 0, which is now, your a is 1. At higher redshifts, a is smaller and smaller. So the things which are closer together at higher redshifts have sort of gone far away. So matter density, evolves with redshift. So omega matter with redshift or with a and z and t, basically a, z, and time are sort of change of variables. They are all of them can be considered as independent variables. They're like one-to-one mapping. So the matter density goes like rho m naught, the matter density now, times 1 plus z cube. As you go to higher redshifts, the matter density increases. Plus, but dark energy is something whose energy density does not change with time. It's some sort of a vacuum density. So that just remains omega, this. And the wavelength of the radiation goes like 1 plus z, and the energy density of radiation is proportional to t to the 4, right? A t to the 4 for black body. So it goes like 1 plus z to the 4. So this is rho r naught to the 4, right? And so this can actually be written as rho cr naught. The total density now is equal to the critical density of the universe now times omega matter 1 plus z cube plus omega lambda. And we can ignore this for most practical purposes. The universe was radiation dominated at redshift around 3000 or higher. But for our purposes, we are really interested in redshift of 10, 20, 30. Radiation can be totally ignored on the cosmological large scale, right? The other thing is this is rho as a function of redshift. So the universe being flat implies that omega matter plus omega lambda is equal to 1, right? So that rho is equal to rho cr naught. Now this gives you how your A evolves with time. So we'll get A dot by A squared equals H naught squared times omega matter A to the minus 3, right? 1 plus z cube is nothing but A to the minus 3 plus omega lambda. And omega lambda is 1 minus omega m. So this is basically how you can solve for how A goes with time, right? So this is just so this factor is sometimes is written as EZ, expansion factor. This is just a function of Z or A. So A dot by A is equal to H naught EZ to the 1/2. So, or E, you can also call it EA, because Z and A are sort of interchangeable. So dA by A, EA square root, right? So EA is just this guy, right? You integrate it out is equal to H naught dt. So you go from, say, time t equal to 0 to present time t. You go from, say, A equal to 0 to some redshift A, right? So it starts with time t equal to 0 to some time t. This is cosmic time, that time t that appeared as the time coordinate in your interval, the relativistic interval that I wrote. This is what will give you A as a function of time. Evolution of scale factor as a function of time. Yes, the time t equal to 0 can be taken as the starting of the Yes. Yes, you can take that as the time of Big Bang. There is a subtlety here which we'll actually not go into, which is something called the horizon problem and all that. And hopefully your other course will get into it, and basically the motivation for inflation and all that. So you know that this integrating from 0 is not a trivial thing. You can have, if you have a non-trivial evolution at very early times, this can actually change in subtle ways, but I'll actually not go into that. So this is not, this is not analytically solvable in general. Actually, for flat universe, it is analytically solvable. So there is this Einstein's de Sitter model where omega matter is equal